Hi, this is Jack McKenna with LandDataPlus.com. This is an introductory level presentation on digital terrain models. Ortho-image generation. Orthorectification is a process whereby, through image resampling, the effects of image perspective and relief displacement are removed. The resulting ortho-image has uniformly scaled pixels that constitute a planimetric map. Input data include aerial triangulation results and a DTM, or digital terrain model. The role of the digital terrain model. Two common forms of DTM are regular grid, DEM, and triangulated irregular network, TIN, TIN. A regular grid DTM has an array of uniformly spaced elevations. A TIN contains elevations acquired at critical points with the added accuracy of break lines. Nonlinear image errors in aerial photographs. Causes of nonlinear image errors include lens distortion, refraction, film development, film distortion, non-planarity of the sensor surface, errors of the measuring device, errors of the film scanner. Lens distortions. They do not degrade image quality. They deteriorate the geometric quality or positional accuracy of the image. They are classified as either symmetric radial or decentering. Radial distortion causes image points to be distorted along radial lines from the optical axis. Symmetric radial distortion. Rectified imagery. Rectified. Generated at a fixed scale and pixel resolution, a simple rectified image contains horizontal errors caused by relief displacement. Image rectification versus orthorectification. Understanding correction methods in aerial and satellite imagery. What is image rectification? Rectification corrects image tilt and perspective distortion. It aligns an aerial or satellite image to a map/grid coordinate system, but does not fully correct relief displacement, used when terrain is relatively flat, quick map alignment is needed, basic geometric correction is sufficient. What is orthorectification? Orthorectification removes both perspective distortion and terrain relief displacement. It uses sensor geometry, ground control points, GCPs, digital terrain model, DTM, or digital surface models, DSM. Results: true map accurate image and orthophoto. Key differences. Rectification. Corrects tilt and perspective, does not correct terrain height effects suitable for flat areas. Orthorectification. Corrects tilt plus relief displacement. Requires elevation model, digital terrain model, digital surface model. Produces accurate scale everywhere. Essential for land administration, surveying, and mapping. Why it matters for land administration. Orthophotos are required for parcel mapping, cadastral accuracy, infrastructure planning, legal evidence, and boundary confirmation. Rectified images are useful for quick visualization, initial planning studies, and urban change detection. Orthorectified images. Orthorectified. When a digital terrain model, a DTM, accompanies the orthophoto, the Z coordinates enable 3D measurements to be made. Building displacement lean can be removed by using the elevation value of the building roof outline. This is an image strip over elevation data. Regular grid versus TIN. DTMs and orthophotos. After aerial triangulation has been completed, it is possible to extract 3D geospatial information. Use of match points in 2 or more images and the photogrammetric math model, the Z dimension, can be calculated. The process of extracting elevation data from a stereo pair of photographs can be either manual or automated. Image matching autocorrelation enables the generation of a uniformly spaced grid of elevation values. Photogrammetric Digital Train Model, QC. It is critical to perform a QC pass on elevations derived through autocorrelation. The massive number of elevation posts generated increases the potential for blunders. It is not unusual for 5 to 30% of elevation points generated to require post-editing. Light detection and ranging. LiDAR, generated DTMs. LiDAR systems produce elevation data, and they can also produce intensity images. LiDAR employs a high-performance inertial measuring system combined with GPS to measure the sensor attitude and position. LiDAR can produce 10,000 to 80,000 points per second. LiDAR DTMs. Continued. LiDAR systems produce multiple returns which are used to discriminate between vegetation canopy and the underlying surface. Multiple returns help to automate the process of bare earth generation. Typical elevation posts are 0.5 to 5 meter spacing. Extensive QC and editing of the digital train model is required. Multiple LiDAR returns. First returns, second returns, third returns, and fourth returns. LiDAR used for change detection after a hurricane. LiDAR change detection. LiDAR building point cloud. LiDAR processing feature extraction. Point clouds. Bare earth canopy removed. QC for LiDAR brush point control. LiDAR QC, tree canopy. LiDAR QC, tree canopy again. LiDAR NSSDA and ASPRS accuracy check. LiDAR for Grand Canyon. LiDAR shading. This is LiDAR images of Manhattan before and after the 11th of September 2001. Mass points and break lines. LiDAR contours with ortho image. Watershed analysis. River 3D perspective. What is IFSAR? IFSAR stands for Interferometric Synthetic Aperture Radar. It is a remote sensing technique using radar from 2 or more antennas on aircraft or satellites to create highly accurate 3D surface models of the Earth. How IFSAR works. Radar signals are transmitted toward the ground. The signal returns to 2 separate radar sensors. Small differences, interference, between return signals are analyzed. These differences allow precise surface elevation calculation. IFSAR outputs. Digital surface model, the DSM, elevation including trees, buildings, infrastructure. Digital train model, DTM, bare earth elevation, structures, and vegetation removed. Orthorectified radar imagery, ORI, geometrically corrected radar imagery for mapping. Key benefits. Accurate elevation data, even in clouds or at night. Works in dense vegetation or optical fields. Cost effective for large areas. Fast collection and processing. This is an IFSAR elevation image. Conclusion. Digital train models, DTMs, LiDAR, and IFSAR are foundational technologies that enable precise mapping, land governance, and modern infrastructure planning. Key takeaways. DTMs support accurate orthorectification and map quality imagery. LiDAR and IFSAR provide high-resolution elevation data across all terrain types. Quality control is essential for trustworthy geospatial products. Accurate elevation data underpins property rights and engineering decisions. Thank you for your attention. Again, this is Jack McKenna. Email address jack_McKenna@landdataplus.com.